Okay, let's start. So, welcome everybody, both in presence and online, to this open lecture of the Master in Philosophy in Lugano. And indeed, this open lecture is part of Tim Maudlin's class that is offered in the context of the Master in Philosophy in Lugano. And so I'm going to start by saying just a few words about the program for those of you that do not know it. I guess that the people present here, most of them at least, already know it. So it is a 2-year master. It is taught completely in English. It is based in Lugano, Switzerland. It requires a bachelor in philosophy. You see 3 dots there because sometimes you also accept people with different bachelors. For example, bachelors in the areas that are nearby the ones that the program focuses on, like, for example, bachelor in physics. This is a typical choice here. It is also accessible as a second master, meaning that if you already have a master, but you want to specialize further in one of the areas or you want to prepare for a PhD, this is also possible. I'm going to present the program very briefly in 4 numbers. The 4 numbers are different from the last time for those of you that were here, and they are this time 51, 20, 26, and 2000. So I'll let you try to guess in your minds, but let's go ahead with them. So the first one, 51. 51. So the program is actually designed to prepare students for PhD applications. And 51 is the number of students who actually, throughout the history of the program, got into a PhD. This out of a total of 62 graduates who actually wanted to pursue an academic career. And this makes up 87% of those people. They have continued with a PhD in various universities such as Geneva, Oxford, the University of Southern California, in Australia, Syracuse, Durham, Vienna, Oslo, and so on and so forth. The second number is 20. 20 is the maximum number of students that we allow to enroll in the program each year. We typically have a little bit less than 20 every year. And each of those students actually is assigned a personal tutor chosen among the 25 professors or collaborators of the program. I'm not gonna name names, but I think that you are gonna recognize some of them from the pictures that I'm showing right now. Of course, this number of students allow us to actually follow those students personally through the personal tutor system, but also in other ways through their 2 years in Lugano. The third number is 26. 26 is the number of courses that are going to be offered next year. You actually can find the list of courses on our website. They are organized around the 4 so-called 4 core areas of the master, which are metaphysics, logic, philosophy of mind, and philosophy of physics. And the 4th number, which is the only number that was already there during the last presentation, 2,000. 2,000 francs is the semester fee. Let me also mention that the students have several funding opportunities in the form of scholarships, reductions of the fees, and also student assistances. In case you're interested to find out more about the program, you can visit our website, drop us an email, or find us on social media such as Facebook, Instagram, X, or YouTube, where you can find recordings of talks, conferences, sometimes, rarely, classes, like the one that we are about to attend, indeed, as I was mentioning before, by Tim Maudlin, and the title is Experimental Phenomena and the Structure of Space and Time. And that's it.
Thank you. Okay, so for anybody who's just dropping in for this one, this is the second class. I'm going to recapitulate some of the main points that I made in the first class yesterday, but of course not all of it. try and tell a reasonably self-contained story today, because some people, that's all they'll hear. This is a course in what's called philosophy of physics or foundations of physics. I would say it's a course in metaphysics, which is just ontology, focused on space and time. And the reason why it's appropriate to do this in the context of talking about physics is that at least one reasonable initial characterization of physics is that it is the theory of matter in motion. This is not the kind of thing that there's an official definition or anything like that. Someone else might provide some other way into the topic, but I think this is a reasonably good place to begin, in the same way that you'd say biology is about living things and geology is about mountains and astronomy is about stars and so on. Physics in general strives to give an account or a theory of matter in motion. If you start here, then, as I said yesterday, there are two targets of analysis. There's the matter part, and if we were to pursue that, we would end up somehow talking about quantum theory, which is an entirely different topic on its own that needs to be covered on its own. The other part is motion, right? If physics is an attempt to account for the motion of matter, one question is what motion itself is. Now, we're going to pursue here a set of, you could call them definitions. Definition isn't the best possible name here. You might say ontological theses, right? Where by an ontological thesis, I just mean a proposal about what something or other really is. One model we talked about last time is, if you ask, what is water? What we think the correct answer is H2O, right? To be water, to be a molecule of water, is to be an atom of oxygen bonded to two atoms of hydrogen. Now that, again, just so you understand the way I use these terms, that's an ontological thesis. It's a claim about what it is to be something. And of course, there's the ontological thesis, which we all know is true, that there is water, right? Water is among the existing things. I hope there's no question about that. Having established that, you can then go on to ask, okay, but what is it? And the correct answer is the one I just gave you. Now, that's doing ontology. And ontology and metaphysics are the same subject, so it's doing metaphysics. Now, you might say, yeah, but that's what they taught us in chemistry class. What are you mean they're doing metaphysics in chemistry? Yeah, that's what I mean. They're doing part of metaphysics. They're giving you analyses of certain things, proposals, well-justified proposals about the fundamental nature of certain things that actually exist. Yeah. Now, if we were to pursue, we can pursue that. Water is H2O. Okay, that's the ontological analysis of water, but that just, as it were, passes the buck, if you will, off to hydrogen and oxygen. What's hydrogen? What's oxygen? Oh, they're atoms, these different, they have these different number of protons. What's a proton? That's a collection of quarks. What's a quark? And then, as we did last time, at least at the present moment, we end there. That's where the story bottoms out, as far as we now know. So these are ontological analyses. When you have an object that exists, but it's a complex object, it's a derivative object, it itself is made of other things, then the appropriate ontological or metaphysical analysis of it is to specify what it's made of and how those things have to be put together to get you one of these things. And you can pursue that as long as you have composite objects. but eventually the thing has to end somewhere. Logically, it might not. Some philosophers like to imagine that maybe this kind of analysis goes on forever, that there's no bottom level, right? And I can't prove by logic there isn't, but good luck with that thesis, okay? Doesn't seem very plausible. Anyway, we certainly normally think it bottoms out somewhere with fundamental items, which are not ontologically analyzable into anything else. And then we have to think hard, well, what kind of a grasp or account is available for these fundamental things? Now, I also mentioned last time that there are two different questions you have to keep clearly separate in your mind, and that will be very central to what I'm going to talk about today, which is that on the one side, we have what we can call, pick up the wrong now, just not calling that. Okay, we've got the ontology, the what is it thing, and again, that's just another name for metaphysics. Metaphysics is another name for it. Where we're asking for an account of what this thing is. And then we have the epistemology part, or again, another word for this in this case, confirmation theory. Right, so this is answering the question, what is it? And then here we have to take up the question, why should I believe you? Someone offers you an analysis, and first you have to understand what the analysis is, right? First you have to understand, get a good grasp of what they're proposing. Having that understanding, you then have to go on to the question, why should I take you seriously, right? And those are two completely different questions. You can have to do a whole lot of work just getting clear about what the proposal is without having even addressed the question of why I should take this proposal seriously. With some people, like Kant or with Leibniz or someone like that, you can spend your whole life just trying to exactly understand this part of it and then kind of forget about that part of it. It's very easy to get caught up in just exposition of what the thesis is and then forget at the end of the day that there's a second question of why anybody should take it seriously. Now, in the case of matter, again, we kind of start out with things that we believe grant exist and are material, like water, or tables, or chairs, or rocks. And then we find that we analyze those as composite, complex objects made of simpler things and run down that chain to the atoms and run down that to the quarks and the electrons and eventually bottom out. And then it gets really strange and hard with understanding what quantum theory is supposed to be saying about those items. But now, today, we're going to take up the other part of this basic definition, the one that talks about motion. What is it? And again, there'll be a chain of a hierarchy of analysis or proposed definitions or whatever you want to say until we get down to a bottom level. And then we'll worry a lot about the bottom level. And we'll also worry about why I believe this. Now, the nice thing, what I'm going to do today is just walk you through a very important moment in this where we begin to get a transition from what you might call a kind of a prioristic or purely logical approach to answering these questions and inject into it an empirical part, an experimental part, a part that comes from just not giving you an argument in words, but pointing out phenomena in the world. So that was something in the title that I gave for this lecture about experiment. the injection, and now it's not really true that this wasn't there all along, but there was certainly some moments where appeal to observation, appeal to observed behavior takes on a very, very, very central role in these kinds of discussions. And historically, you can find this happening certainly with Galileo. There was earlier work that Galileo himself was building on, and you see it happen with Newton, which is what we're going to talk about today. Newton is a particularly careful person conceptually. He displays the virtues you want out of a good account of this. So good philosophy, if you will. So let's just start now. Motion itself, if you just stop and think for a second, it's a kind of derivative or complex thing. If I try to, if I ask, well, what is motion? Now, I should be a little more precise here, although I'm sure you'll understand what we're really talking about is also commonly called locomotion, right? And there might be kinds of motion, something you might want to call motion, that is not locomotion. Certainly, there are kinds of changes that are not locomotion. At least not obviously when the leaves change color, right, in the fall. That's a change, but it's not obviously a locomotion. And what I had in mind here in the theory of matter and motion, the first thing that should come to your mind is locomotion. Now, it may turn out in the long run, you've got to adjust that too. I mean, all of the stuff is up for grabs, but we have to start somewhere. And here's where we're beginning. So you say, right, well, what do you mean by locomotion? And then again, I don't know if you want to call this a definition, an analysis, whatever you want to call it. The first thing that's going to come to your mind is something like locomotion is change of place with time, right? I mean, somehow if there was an object and you said, no, it's not changing its place over a period of time, you would normally say, oh, so it's not moving, right? It's not locomotive. If someone were to insist, no, it is, right? It is not changing its place over time, but nonetheless, it is moving, it is locomotive. You'd be within your rights to raise a question, right? You'd be within your rights to ask them to say a little more about what they have in mind, because at least at first hearing, it sounds like they've just contradicted themselves. All right. Well, now we again play the same game. So change, motion is a kind of change, but not just any change. What kind of change? A change of place with time. All right, now that gives us two more targets. What's a place and what about time? So of our the two main topics we want to talk about today, where this thing seems to come to the end, that's one of them, time. There has to be some kind of temporal structure for there to be locomotion. Has to be some kind of temporal structure for there to be change in the normal sense, right? Now, again, I'm just going to say this. The word change, like any word, can be used in various metaphorical ways and so on. And there, someone might say, no, there can be change without time. What do you mean? Well, the Alps change in height from east to west. And you understand what someone means when they say that, but that's, of course, a metaphorical extension. Because someone, you might say, look at the time scales we're worried about. The Alps don't change their height. I mean, you can kind of work out what they're trying to convey by that use of change, but it's not this kind of central use, right? All right. So we have to, so change itself, right, involves time. So we're going to have to get a handle on the structure of time and the nature of time. And since locomotion is change of place, we're going to have to get a handle on what we mean by the place of something. What does it mean to say that it has a certain place, or the place now is different than the place it had a little while ago? Now, place, I mean, I'll just jump here. You all now have a copy of this, the Newton's Scholium on space and time from the Principia. And I'm going to go through fairly carefully, and because there's some people who are just tuning in, I'm going to liberally just read it. So if you haven't had time to read it, you'll understand what Newton's saying, large parts of it. So I will just read the beginning, right? Hitherto, this is a scholium that occurs after Newton has defined 8 different terms. So there are 8 definitions, 1 through 8, where he's defining technical terminology like quantity of motion and so on, motive force, various things that are not terms that don't come up in everyday life. And then after that, he says, I have laid down the definitions of such words as are less known, and explained the sense in which I would have them be understood in the following discourse. I do not define time, space, place, and motion. All right, so the scholium is about 4 concepts that he lists out: time, space, place, and motion. Right, so he's got on his list things that have already come up. He also mentioned space, which we haven't exactly brought up directly here, but it'll come in. I do not define time, space, place, and motion as being well known to all. Only I must observe that the common people conceive of those quantities under no other notions but from the relation they bear to sensible objects. And thence arise certain prejudices, for the removing of which it will be convenient to distinguish them into absolute and relative, true and apparent, mathematical and common. So we've got 2 notions, okay? And each then 3 contrasting pairs of terms. So on the one hand, we're going to have absolute, true, and mathematical time versus relative, apparent, right? Is that, yeah, apparent and common time, right? Well, time and space and place and motion. So for each of our 4, there'll be a version that's this, which is what the common folk use, and a version that's this, which is what Newton's using. And he doesn't want you to get confused here. Now, there are a lot of things going on here. I'll just briefly note. Again, Newton is perfectly aware of what he's doing. If you thought your job as a philosopher, which was kind of the rage at a certain time, was to analyze everyday language, then you'd say, well, really, my job is over here. This is the everyday language, right? This is the man on the Clapham omnibus, as they say, or the person in the street when they talk about what time or where am I, okay? Or am I moving or whatever. What they have in mind, Newton says, is over on this side. But in his book, he doesn't care about that. He cares about this. Why? Well, there are going to be arguments for that. The main argument is pretty simple. You can't do physics in terms of this. It's just, these are not the concepts in terms of which physics can be framed. You can only do it in terms of, yeah. Now, one can say that, and there's a, you know, and that's correct. Of course, between these two sides, you also notice that over on kind of the, I mean, you know, the bad side or the more disreputable side or the sleazier side, whatever you want to call it, right, is sitting a parent, which is really the same as observable. That kind of motion, that kind of place is something you can see. And this you can't see. So that already means that Newton can't completely leave behind this side of the equation. Or if he does, then he can't do what I'm going to show he does, which is appeal to observation and experiment to defend his account of space and time. And there are, and he talks about, there are relations between these, and he talks about them. We'll get into them. Now, there's some terminology here, which if you've done a lot of philosophy, might be familiar to you, and I just want to highlight that before I go on, which is up at the top, this one, this pair, the absolute relative distinction. And relative, okay, there are subtle differences in meaning here, but relative is really closely related to the idea of relational, right? And you might hear in the philosophical literature a lot about absolute versus relational theories of space, absolute versus relational theories of time. And if you want some figures to associate with them, the obvious ones are over here, the great defender of these absolutes is Newton. And on the other side, the great defender of the relational theory, the denial of absolute space and time, the denial of Newton's account, is Leibniz. Okay, so you have two titans fighting against each other. Newton arguing that this is the correct and deep account of space and time, and Leibniz arguing that, as it were, the correct account lies more on this side. Now, let me just say a few words about things we're not going to spend a lot of time on. If you're interested in this, the first thing you need to read is the Leibniz-Clark correspondence, which occurred right toward the end of Leibniz's life. He got involved in an exchange of letters, not a direct exchange, but an indirect exchange of letters through an intermediary, Princess Sophie, I think, where Samuel Clark was Newton's representative. Newton did not get directly involved. There are people who think that at a certain point, Newton got himself involved and sort of whispered in Clark's ear and said, "Look, buddy, you're not saying the right things." And I should also say, just if you're prepared, if you look at it, this does not start out as a discussion of space and time. It starts out about, it really starts out and gets hot because Leibniz says that Newton's philosophy is promoting atheism and materialism. So it's a religious, right? It's kind of a big religious fight. And Clark steps in to defend Newton from this charge. And in the course of their exchange, which goes over 5 sets of letters, for kind of funny reasons, an example having to do with motion, and it comes in, and Leibniz directly attacks Newton's theory of absolute space and time. Clark doesn't really give the correct answer until about the fifth letter, which is strange. He should have brought it up earlier. Leibniz gives a very weak response. I guess that's about the fourth letter. Leibniz responds. Clark is ready to respond. And Leibniz does the ultimate thing you can do to not lose an argument. He dies. So that's the end of that. So there's no more, at exactly the point where it seems to me he has Leibniz on the ropes. Leibniz exits the scene. So, I mean, what we're talking about, even though it's obviously deep in the history of physics, it's also deep in the history of philosophy. I'll say one other word. I don't want to get drawn too deeply into this. The theory of space and time, the account of space and time in motion that Leibniz is defending in that exchange, isn't really his deep, deep theory of space and time. So he has an even deeper theory, which is tied up with the monadology and so on. It's very, very complicated and weird and involves pre-established harmony and all kinds of stuff that doesn't really come up in this exchange. So this is sort of medium level, middle level Leibniz. And there's an even deeper, stranger theory that's underlying that one. That would take us way too far. When people associate the relational theory of space and time with Leibniz, they mean this theory. They don't mean that. Okay. So, we have motion, we have time, we have place. And as I said, there's a fourth concept that's going to come into this, which is space. And that's, the main topics of this class are time and space. Newton says, I need, there are these versions of these four things and these versions of these four things. Let's distinguish them. So now, again, if you haven't read it, I'll just read what he has to say about each. Absolute, true, and mathematical time, of itself and from its own nature, okay, of itself and from its own nature, so without having to bring anything else into the story, flows equably without relation to anything external, and by another name is called duration. Okay? Now, again, I can stop and say Newton uses a famous word here that many people have worried about, that time flows, and furthermore flows equably. And people have rightfully worried about what that could mean. That part I'm not going to worry about so much. I'm here. Later we'll come up with that. The main thing here is that he's saying absolute, true, and mathematical time has its structure without relation to anything else. You don't need anything else to have time. As opposed to what? Well, let's look at relative, apparent, and common time is some sensible and external, whether accurate or unequable measure of duration by the means of motion, which is commonly used instead of true time. Such as, and these are examples of relative time, an hour, a day, a month, a year. Okay? So let's just stop and see what he's saying here. He's saying, look, when I ask you, someone asks me what time it is, what do? I look at my watch. Of course, at Newton's time, you might look at a sundial or whatever. Might track the positions of the stars to figure out what time it is. That's obviously observable and involves matter. involves some kind of visible or tangible material thing. Whereas absolute, true and mathematical time doesn't depend on it. Okay? Now, if you hang around in foundations of physics, and especially if you even listen to physicists a bit too much, you'll often hear the following phrase when if you ask a physicist or a certain kind of philosopher, well, what is time? That sounds deep, right? That sounds profound. What is time? And then you'll get maybe the following sentence. Time is what clocks measure. Okay? As if this answers, presented as if it answers your question. Now, I have to say, quite honestly and directly, that some physicists take this really, really serious. For example, Roger Penrose, who recently got the Nobel Prize, has a kind of unorthodox theory of cosmology called cyclical cosmology. I'm not going to go into the details, but part of it involves him claiming basically that if at a certain point in the universe there are no clocks, then there's no time. Now, by a clock, even an atom, right, could be a clock, anything that behaves in certain, but he thinks that eventually, if all of the matter decays into light, and there's no matter around, so you can't make a clock, then time itself is gone, or at least a certain feature of time itself no longer exists. That idea is a certain reading of this claim. I mean, a reading, as philosophers, we might say, it's the question, what is the nature of this is in this sentence? And as philosophers, we are aware that is can be used in many ways. As Aristotle said, it is said in many ways. And we have a certain way that just to indicate it, we can sometimes do this, equal df, right? That kind of is means this is the definition of time. This is, and if that were true, then if there were no clocks, then obviously there would be nothing that clocks measure because there are no clocks. And if there's nothing that clocks measure, and this is the definition of time, then there is no time, right? It's a short and sweet argument. However, it's nonsense, right? Because this is not the definition of time. If anything, it's a definition of clock. What makes something a clock? A clock is an object designed to measure time, right? As opposed to a thermometer that is designed to measure temperature, right? It would be as silly as saying if there are no thermometers, then there's no temperature anymore. Notice, I mean, this is also pretty explicit. Remember, what Newton says here is that absolute time of itself flows equably without relation to anything external, right? That is, without relation to any clocks, without relation to anything visible, without relation to any matter. Time itself flows equably. And when he talks about the observable measures of duration, he says, apparent time is some sensible and external, whether accurate or unequable. Now notice the inaccurate or unequable. I mean, just think for a minute. You say, how do you know? You're telling me this is not this is of definition, right? I mean, if you want an is of definition, this should be a clock is equals by definition a device designed or intended or something. I mean, it's real to measure time, right? So that's where the definitional part comes in. You're defining clock. But think about clocks, right? I mean, here we are in Switzerland. You should think about clocks, right? You should think about the amount of effort and training that went in to attempt to make better and better and better clocks and watches. What do you mean better? More accurate. Well, what do you mean more accurate? I mean that more closely indicate the actual amount of time that has passed. The actual amount. I mean, if the definition were here, right? If time by definition is just whatever clocks measure, then by definition clocks would be accurate. They'd be perfectly accurate. Because they sure measure whatever they measure. Right? I mean, it would be kind of contradiction in terms to say a clock runs slow, or a clock runs fast, or a clock sometimes runs slow and sometimes runs fast. Because you say, well, what do you mean? After all, time is just whatever the clocks say it is. But that's ridiculous. Right? We all know it's ridiculous. That's not what, you know. The idea is that there is out there in the world, independently of my clock, a quantity. How much time has passed. And what we want to do when we build a good clock is make a device that gives visible indicators that are accurate. Where when the clock says an equal amount of time has passed between this and that and that and that, an equal amount of time has passed between this and that and that, right? Where the second part is over here, right? The absolute time. I mean, that's just the way things work. Now you can say all of that is confused and so, but understand if you object at this point, you are now bringing in a very new set of concepts that are quite contrary to even everyday concepts of what clocks are, what they're attempting to achieve. Okay, so we've got time, and then he says an hour, a day, a month, a year. And you know what he means. I mean, how do we make judgments about how much time has passed when we were trying to be accurate? Well, again, we can make clocks, or initially we use the rotation, essentially the rotation of the Earth. How do we do that? Well, you track the sun, and every day when the sun reaches the highest point, you call that noon. And then you say a day is the period from one noon to the next noon, and then you divide that into 24 parts and call those hours and so on. Yes? Now it turns out if you do that, by the way, and they knew this, that's a pretty good clock. It's not a great clock. Right? The length of a day changes, as I've just defined them. Right? The period from noon to noon changes over the course of the year. Which has to do with the orbit of the Earth. If you want to do a little better, and you can do a little better, you don't track noon to noon. You pick a star. Right? You don't use the sun, you use a star. And you mark when the star reaches a certain elevation or position. And then the next time around, and then the next time around. That's called ephemeral time. Doesn't use the sun. That's much better. That's what astronomers use. It's more accurate. Because the amount of time doesn't vary over the course of the year. An ephemeral day is about 23 hours and 56 minutes. The extra 4 minutes have to do with orbiting the Earth. Okay. Anyway, doesn't matter. So yeah, that's what Newton says. That's a relative, common, and observable time. Ephemeral time, noon to noon. These are things you can just go out and look for and measure and see. But you can't directly see time, right? You can't directly experience it. I mean, this is the puzzle you have, that time exists in some sense, but you can't directly see it, right? You can't directly experience it. So how do we know it's there at all? Or why should we think there is such a thing? Yeah.
Might it not be kind of under the assumption that time is not in fact identical to some of the measures? Because if you do believe that time is essentially just the measurements of time, then you do experience time.
Well, I mean, okay, so you, again, the words that you just used are, of course, a little problematic. Time is a measurement of time, right? Because then you say, but that second time, what is it? Oh, that's a measure of what? Of a measure of, now I'm going to unpack that and get an infinite string of x is a measure of x, x is a measure of a measure of a measure of a measure of a measure of, with no end to it. The question is, if you want to say, look, what is, if you want to choose one of these measurement techniques, like ephemeral time, and you say that's time, right? Time just is. Equal time is the period from the reappearance of a star in the same location. You can try that. You notice what happens immediately. Newton would notice this, any physicist would notice it. By that definition, the Earth can't slow down its rotation. Because by definition, it's always the same amount of time for one complete rotation. But of course, the Earth does slow down its rotation. In fact, we know it slows down its rotation. We know it, and we know it's slowing down its rotation as we speak. I mean, we know the reasons it slows down its rotation. You see, if you try to promote any of these methods of measuring time, not as a method of measuring, which can be more or less accurate, but a definition of time itself, whichever one you pick, there are going to be objections, and very good objections, about how that particular method it can be, and sometimes is, inaccurate. But of course, inaccurate means there's a standard that you're aiming at that you're not quite achieving, and that standard is defined over here. And this is Newton's view. And what I'm arguing here is it's not just Newton's view, it's the way everybody thinks about it. Because if you try to get rid of time in favor of clocks, you have this real difficulty. I mean, you also have the difficulty, again, if by a clock you mean anything normally we recognize as a clock, you start doing cosmology and you go back and say at a certain time, everything was hot and it was a plasma and it was blah, blah. And you say, hey, it couldn't be any clocks, right? No clock could survive that. There's nothing like a clock. Okay, then there's no time. Time's gone. That's not right. You see, the whole idea of measurement, we can go into, in fact, a very important concept here is measurement. Because the fundamental concept of a measurement is that there is a quantity out in the world that you're trying to find out, right? You're trying to determine what it is. And so you try and set up a situation where you can see something that will tell you what it is. But for it to be a measurement, there has to be something out there independent or antecedent to your procedure. The thing your procedure is trying to get its hands on, right? When I say I'm going to measure my weight and I step on a scale, the assumption is I have a weight before I step on the scale, right? And if it's a good scale, it'll give me pretty good information about what that weight is. Now, if somebody says, no, weight is just whatever the scale says it is, then what I'm doing when I step on the scale isn't measuring anything. It's, I don't know, creating the weight, bringing it into existence. You know, here's a novel weighted diet, break all your scales. The normal thought is that doesn't change your weight, just changes your access to it. This particular problem, again, I want to stay away from it because it's a complete mess. It, you know, blossoms out in quantum theory when people talk about measurement. So badly, John Bell wrote a very nice little piece called Against, quote, Measurement, right? Which is, well, it wasn't that he was against measuring things, he was just against using the word measurement the way physicists use it. And his main complaint is that the concept of a measurement involves the idea that there is some quantity out in the world that you're trying to get information about, right? Otherwise, you're not measuring. But most physicists, when they say, I do a position measurement, say on an electron, and then you go and ask them, oh, before you did it, was the electron there? No, electron wasn't anywhere, right? You'll hear these weird things. The electron had no location before I measured its location, but then you couldn't measure its location because there was nothing to measure, right? What you're really suggesting is that you did some strange procedure that located, that actually created a location of the particle, right? It didn't find out where it is, it somehow made it. You know, and physicists will say you make it choose, right? You sort of force the electron to decide. So, you know, all this talk, it doesn't make any sense. If you want to say that's what your procedure did, don't call it a measurement. It isn't one, right? It is a position creation operation, right? A momentum creation operation, not a momentum measurement. This is just part of the concept. Now, you can say what you want. I mean, you can make some radical proposal, but don't dress up your radical proposal or put it in everyday terminology that contradicts what you're proposing, right? That's the main point. So Newton is thinking of measurement in the normal way here, right? When I measure X, there was an X there antecedent to whatever I did. And it's a good, a better or worse measurement depending upon how accurately or inaccurately it's giving the information. But the measurement doesn't make the thing, right? Yeah.
I'm having a hard time with something. And I think you're having able to follow what you are saying. And I think I can also follow kind of how cognitive integrity for saying so, or the portraying of the Newton. What I'm having a hard time kind of grasping is how, probably super naive, but how come a parent is in a position, well, not in a position, but in which sense a parent is in a contraposition with true, because when it comes to absolute and relative, the opposition seems kind of obvious, and it's a given, saying this conceptual given. When it comes to mathematical common, it's also kind of intuitive to follow, especially the last part of measuring. Yes. When it comes to the pair true and apparent,
right?
I'm having a hard time, because if we go with the notion of apparent as something that it's not necessarily the case, or maybe the case and may not at the same time, that also allows you to have at least the possibility of truth. So I'm not so sure in which way.
Right, I understand what you're saying, but I don't, that's not, I think, what Newton means by apparent here. I think what he means by apparent is, just be visible or perceptible. Right? something that is apparent in this sense is something that your senses get a grasp on.
Well, I mean, if that's the case, but my surprise have to do then with, if we are assuming that that's the direct opposition with truth, then how do we establish the empirical rule in order to kind of confirm or refute this?
You're following the structure of this lecture perfectly. That's right. That's right. I mean, that's what I'm going to get to. That's what you have to understand goes on in this Scholium. That, as I say, Newton clearly says physics is in terms of these. Physical laws are stated, specified in terms of these quantities. But he also brings into the discussion experiment, which means visible, perceptible stuff, which lies over on this side, right? So it can't be that you just, as it were, take all this and throw it away. No, there's a relation between these two. He's going to talk about that. And he's going to talk about how you can use experiments to provide evidence for this structure, even though this structure is not itself directly perceptible. Okay?
Are you suggesting that Newton was kind of the precursor of metacognitive analysis about how scientific research pertains to may work?
He was a smart guy. I mean, if you want to say he was the precursor of metacognitive analysis, look, what he's doing makes perfect sense. And when we get to the end, you know, when you read this and you see what he's done, it all hangs together. Now, you might come and try and give a more nuanced account of what he did, and it might go in the direction you're saying. He knew what he was doing. You know, I mean, Newton, we could do the same thing in another class about light. What is light? People knew from antiquity there was light. What is it? Is it a particle? Is it a wave? Blah, blah, blah. What did Newton do? He writes the optics. What did he do? He goes into a room and he blacks it out and he has a little beam of sunlight come in and he has a prism and he uses the prism to divide it into colors and then prisms to check whether the colors divide into further colors. All of this experimental, empirical activity on the basis of which he's arguing in favor of his theory of light. So yeah, I mean, you absolutely cannot leave this side of it behind, even though from, as it were, deep ontological or metaphysical perspective, this side is the real, is the important stuff. And how you negotiate that, that's exactly what this talk is about. If I can't see absolute time and absolute space, right? I mean, we can do the same thing. Let's just do space. Let's move on. So absolute space in its own nature, without relation to anything external. So again, no matter, no nothing, just space all by itself remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces, which are sense determined by its position to body. So again, the relative positions we determine by sense. That's where the empirical stuff comes in, right? Such as the dimension of a subterraneous and aerial or celestial space determined by its position in respect of Earth. Absolute and relative space are the same in figure and magnitude, but they do not remain numerically the same. For if the Earth, for instance, moves, a part of our air, which relatively in respect of the Earth remains always the same, will at one time be in one part of absolute space into which the air passes, and another time it'll be in another part of the same, and so absolutely understood, it'll be continuously changed. Now, let's just go back. I mean, you can see the structure of his talk of absolute space parallels, in a way, the structure of absolute time. So let's just go into that, right? I mean, often when I start this lecture, I would actually start in a more commonsensical way, right? So let me do that for a minute. So I asked, just, don't be fancy about it, right? Right now, what's moving? Right? What are you aware of that's moving? Somebody. This is an easy question.
You.
I am. Right? I'm moving. Okay, that's the everyday answer. Now, why? I'm constantly changing my location. What do you mean changing your location? Look, you're getting closer to that wall, then closer to that wall, then back closer to that wall again, right? My relative position with respect to the walls of the room is changing, whereas for most of you, it's not changing much, and for the tables and chairs, it's not changing at all, okay? So we start there. That's the naive answer. That's the everyday answer. That is on this side, right? This is what the common folk take motion to be. Now, and I just want to pursue this because the following question I'm going to give you can be pursued in two completely different ways. So I say that's the everyday simple first answer. What's moving in this room? I'm moving. You're not moving. Now, I say, no, don't be naive. Don't give me the everyday man on the Clapham omnibus, unwashed herd answer. Give me some sophisticated answer, right? From a sophisticated perspective, what in this room is moving? Somebody be sophisticated. Yeah.
I don't know if this sophisticated because this goes in the wrong place, but it's relative, right? Like that Galileo says that sort of have this idea of relative velocity.
Okay, so if one were to go, again, there are two ways to be sophisticated. You just gave one of them. Okay. There's another way to be sophisticated, but let's put the first one down on the board. Okay, so sophisticated answer one. These things work now. Sophisticated one. It's all relative. And this is so we can call this relationism, if you will. You say, look, I can't answer. The only kind of answer is X moving has. You haven't asked me a full question. The full question is X moving relative to Y? Some Y. Right? It's like saying, if I just said out of the blue, is that tree to the right? And you say, well, you haven't even asked the full question yet. To the right of what? And from what perspective, right? This is not like, is that tree taller? Taller. Taller than what? If you say that one, it is taller. You say that one, it isn't taller. I mean, Socrates already talks about this. This is a fundamentally relational thing, and that motion is fundamentally relational, and therefore, until you specify with respect to or in relation to what, you don't even have a question, is it moving? Right? That is, as it were, the essence of the Leibnizian view. So what would that say? It would say, well, right now, we're all moving and not moving. Right? Nobody's moving relative to themselves because you're getting no further or closer to yourself as time goes on. But right now, I'm moving relative to you, right? But equally, you're moving relative to me. And we're all moving in a funny way relative to the car going by out there, and in a different way relative to the bird flying by over there, right? Because our relative position is changing. Relative motion, by the way, the first thing to notice about relative motion is that it is symmetric. If A is moving relative to B, then B of necessity is moving relative to A, because relative motion is just change in the relation, and the relation holds between A and B. Okay? And so if you follow out this line of thought, where do you end up? You say, well, nothing's really moving any more than anything else. Everything, in a way, is moving always in an infinite number of different ways and not moving at all times. Right? That's where you end up with if you just take this kind of untrammeled relationist view. This is a view that elsewhere Newton directly attacks. He attributes it actually to Descartes at that point. And he says, look, that's why you can't do physics with relative motion, because nothing has a unique relative motion. It has an infinite number of motions at all times. So how could there be laws of motion? Let me take another couple steps in this direction and we'll get close to what Newton's real target is, one of his real targets in the Scholium. Now, if you were to say that to Descartes, you say that to Aristotle, this really goes back to Aristotle. Those relationists had an answer, and the answer was no. Motion isn't just relative motion with respect to anything. Motion is the motion of an object with respect to its immediate surroundings. Okay? To what's right next to it. So, now I'm not moving. Why? Because I'm not moving relative to the blackboard, whiteboard, which is the thing that is immediately at my edge. Right? And now I am. I think I'm too far on the race. Okay, now I am moving. Why? Well, it's relative motion, relative with respect to what? Relative to with respect to the whiteboard. Why is the whiteboard relevant? Because it's the thing that's immediately next to it. Okay? That's the view, that's the version of relationism. I mean, it gets out of this problem of saying there are too many relative motions. That's the relationist view that is Newton's target in Scholium. Right? He's going to give you reasons to reject that view, which he associates correctly with a whole tradition that certainly it was what Descartes himself was explicitly defending. It's a little subtle what Leibniz was doing, okay, but you can trace the Cartesian thing back to Aristotle for sure. Parts of Aristotle. So that's a kind of relational theory of motion. And so how did we get to motion? All right, so let me, actually, I skipped over. So we had four things, right? Time, space, place, and motion. So what's place? Well, place is, once you have space, you have relative space, you can say relative position. The place is that part of space the thing occupies, right? That's its place. So once you have the space part, the place comes along. And then motion is change of place, right? Locomotion is change of place. So you're locomoting if you're changing your place. If it's a relative place, then you're locomoting when you're changing your relation to some object. If it's absolute place, then you're locomoting when you're changing your location in absolute space. But absolute space, as we say, is not observable, right? Okay, so I just followed out one sophisticated answer to what's moving now, which took us in the direction of relationism and relativism, right? Does anybody else have a sophisticated answer, a different kind of sophisticated answer to the question, what's moving in this room now? Yeah.
Whatever.
So what, I mean, give me an example.
Okay, so if I start, no one is running to the, basically everyone is sitting in their place, nothing special is happening. But if I were starting to run
Okay, but even as we're sitting here, let's take the running out of it. As we sit here,
Accelerate towards the earth.
well, I'm not right now accelerating toward the earth. I am accelerating. For anybody who knows this stuff. Why? You're all accelerating that. Why?
It's going around the sun.
That's one. There's a faster one. Because the earth is spinning. Right? The earth is spinning on its axis. And we're spinning with it. There's no relative motion between us and the surface of the earth. That's Newton's point. That's a relative motion. We could take the earth as it were the reference. We're not moving with respect to the earth, but the earth itself is spinning on its axis. And we're spinning with it. Now, everybody understands that's true, right? You probably haven't thought too much about it because it's kind of an astonishing thing when you do think about it. How fast are we moving because of the spinning of the earth? Well, if we were on the equator, we'll do the easy one. If we were on the equator, it's about 8,000 miles diameter of the earth, okay? And you're going around once, which means the diameter is 8, so the circumference is about 24,000 miles, and you're going about 24 hours, so about 1,000 miles an hour, right? Faster than the speed of sound. If you're just standing on the equator, that's pretty fast. And that doesn't count the other one. The earth itself is orbiting the sun 93 million miles away. Now you're going, thousands and thousands of miles. Because, you've got to go all the way around in a year. I mean, the speeds are quite astonishing. This was, of course, as everybody knows, the objection to Copernicus, the objection to the Copernican theory, which took the Earth out of the center of the universe and stuck the sun at the center, anyway, in the solar system, and had the Earth both spin on its axis and orbit. And people said, well, wait. I mean, if we're spinning every 24 hours and we're going, I don't know, here, maybe we're going, 500 miles an hour or something. How do the birds keep up, right? Why is it that when a bird lets go with its little claws from a tree, it just, it can't fly that fast? Why is it that if I drop a heavy object off of a building, in the time that it takes to fall from the top to the bottom, you're telling me everything's moving 500 miles an hour. Why doesn't the ball fall way, way, way far away, right? And then Galileo had all of these answers. That he will go into a ship that's moving, and you'll notice that these effects don't occur. So it doesn't work that way. Now, Galileo was never entirely clear about how it did work, but it didn't work that way. Now, this is the Newtonian answer, right? Newton would say, sure, we're all moving, for sure, absolutely moving. Why? Because the Earth is spinning, at least. Now, Newton's that view pushed that direction also is quite intuitive, right? It's not a weird view. I mean, I like to illustrate the view with a little fictional story to make the point. And this is now going the other direction. This is going toward Newton's account. So one day you're in Dallas, Texas, and you're down on Dealey Plaza. And it turns out there was somebody there who's just an absolute obsessed with John Kennedy's assassination and spent all his time studying the assassination. And you see him, and he goes to a certain spot in Dealey Plaza, right? Looks around him at the buildings and says, oh, this is the spot where the assassination, I've studied it all my life, and now I'm standing in the spot where the assassination. I mean, I had a similar effect when I was young. I was in the Agora on a thing, and we were going around, and I was with an archaeologist, and we stopped in one of the ruins, and he says, it seems as though from all the information, you're now standing in the place where Socrates died. Okay, this was the jail cell. amazing kind of thing. Anyway, so this guy says, now I am standing where Kennedy was assassinated. And, this guy on the sidewalk looks over and says, no, you're not. I mean, what do you mean, no, I'm not? He says, no. Kennedy was assassinated in November. It's June. The Earth was way over there, right? When Kennedy was assassinated. Oh my God, you're right. I want to be in the very location where Kennedy was assassinated. Comes back November 22nd at exactly 12, whatever it was, and stand there. Now I am in the spot where Kennedy was assassinated. The other guy's still standing. He says, no, you're not. What do you mean? The galaxy's rotating, right? The whole solar system has been moving. We're now way, Kennedy was assassinated way over there, right? Very rich guy, so he builds a rocket and does these fancy calculations and gets in his rocket, goes to a certain spot. I am now where Kennedy, the Earth and the whole solar system is way over there. I am now in the spot where Kennedy was assassinated. The other guy, who's also very rich, pulls up in his rocket. No, you're not. The galaxy itself is moving, within the local galaxy group. And it was way over there. Now, the question is, and you see he has a point, right? I mean, it's not like this is just silliness. The question is, does this end? Now, Newton thought it ended, right? Newton thought there exists today a location in absolute space where that event occurred in 1963. All right, there is such a place. And I think he'd be pretty sure it isn't here. But then you say, but how do you know? How could you ever find out where it is? I mean, there's no mark, right? There's no visible, apparent, observable mark left over from that event that would allow you to identify. Right? Now, Newton, so that's the Newtonian view. If you follow out again, these markers don't work anymore. So we have the absolutist view, sorry. So there's a kind of sophisticated relationist view or relativist view. I just can't write anymore. And there's a sophisticated absolutist view. Okay. So there is an absolute location where events occur. And what it is for an object to be absolutely moving is to be changing its location in absolute space. And that has nothing to do with anything visible or observable or apparent in this sense of apparent. Now, it's not that Newton is unaware of it, right? So again, let me just quickly read the last two definitions. Place is a part of space which a body takes up and is according to the space either absolute or relative. And then if we skip down to 4, absolute motion is the translation of a body from one absolute place into another, and relative motion, the translation from a relative place into another. Right? Thus, and this is kind of his version of the Kennedy thing, thus, in a ship under sail, the relative place of a body is that part of the ship which the body possesses, or that part of the cavity which the body fills, and which therefore moves together with the ship. And relative rest is the continuance of the body in that same part of the ship or in its cavity. But real absolute rest is the continuance of the body in the same part of that immovable space in which the ship itself, its cavity, and all that it contains is moved. Wherefore, if the earth is really at rest, the body, which relatively rests in the cavity, in the ship, will really and absolutely move with the same velocity which the ship has on Earth. But if the Earth also moves, which it does, right? If the Earth also moves, the true and absolute motion of the body will arise partly from the true motion of the Earth in immovable space, partly from the relative motion of the ship on the Earth. And if the body moves also relatively to the ship, its true motion relative to the motion of the body on Earth. And you just go through, if the sailor's walking this way on the ship and the ship is moving that way relative to the earth and the earth is moving this way relative, to absolute space, you pile all these on top of each other and you get finally the absolute true motion of the sailor. Right? He's moving east relative to the ship, but west relative to the earth, but east, but it ends with absolute true motion. And then, he talks about how absolute time in astronomy is distinguished from relative by the equation of correction of apparent time. Again, apparent time is the observable time. That turns out not to be the right time to put into the equations. You have to make corrections to get to the absolute time, to get how much time has really passed between this and that. Now, if you go on the second page, the second full paragraph, I just want to insist how aware Newton is of this situation. He says, but because the parts of space, so you get the idea, right? He believes there is an absolute true in mathematical space, an absolute true in mathematical time. These exist independently of matter. They exist independently of anything observable. They exist independently of any clocks or any measuring rods or any systems of reference or any anythings. Okay? And he says, but because the parts of space cannot be seen, right? You can't see them, or distinguished from one another by our senses, therefore, in their stead, we use sensible measures of them. For from the positions and distances of things from any body considered as immovable, we define all places, and then with respect to such places, we estimate all motions, considering bodies as transferred from some of those places into others. So instead of absolute places and motions, we use relative ones. And that, notice now, and that without any inconvenience in common affairs, right? That's good enough for everyday life. Relative, apparent, and common space, time, place, and motion are good enough for everyday affairs. But in philosophical disquisitions, here we go. In philosophical disquisitions, we ought to abstract from our senses and consider things themselves distinct from what are only sensible measures of them. For it may be that there is no body really at rest to which places and motions of others may be referred. So now you see the bond, right? In everyday life, we use these concepts, and they're good enough. In doing physics, we have to use these concepts. But that means they're not observable, not directly. But physics is based on observation, and what Newton's going to do is give you an argument from observation. So how can that work? Right? How is he going to bring experiment into this discussion? Because he's going to use experiment to defeat Leibniz, to defeat the relations, to say the relationism cannot be the correct theory here for empirical reasons. Okay, well, I've been going on. It's about 4. Why don't we take a 10-minute break? So, and then we'll see what he does. Okay, then we'll do the second part. Okay. So just to sum up the fight we're about to have. And again, this fight that I'm going to talk about is between two quite specific views. And those two views are not the only views you could have, right? I mean, I'm gonna look at a specific version of a relationist theory, the one that Descartes actually held. So it's not a straw man in that sense. And a specific kind of absolutist or non-relationist view, the one Newton held. But there are other kinds of absolutist views as well. Okay, so what we have here are two representatives of types of theories of space and time and motion. Newton representing an absolute kind of approach, and Descartes a relativist or relationist kind of approach. Now, Descartes, Leibniz is a relationist, maybe of slightly different stripe than Descartes. And there are different ways you could realize these basic ideas. But right now, you see what they, and again, it's not that Newton denies that relative motion exists. He says, of course, relative motion exists. And in everyday life, when you say something's moving, you're probably thinking of some relative motion. Right? You're implicitly choosing an observable object as the reference. And the motion you have in mind is motion with respect to that, just as when everybody said, I'm moving now, what you're doing is implicitly taking the room, right? The walls of the room as your reference. And you mean I'm moving with respect to the walls of the room, which I am. Newton doesn't deny that, of course. But Newton says, in addition to these relative and apparent motions, there is absolute motion. And the absolute motion is defined as a change of the location of a body in absolute space. And absolute space is not directly observable. So absolute motion is not directly observable. This is, by the way, again, this is a little bit to see the background. This is a kind of thing that Galileo had already very persuasively argued for. Galileo did not believe in a relational theory of motion. Actually, if you read him, he clearly believed there was absolute motion. He thought the Earth was absolutely spinning and absolutely orbiting the sun. Right? He thought that Ptolemy was wrong when he said that the Earth is at rest. But Galileo, then when people, as I said, people objected, as if the Earth is spinning, look at how fast it's spinning, look at how fast things are moving. If it's orbiting, look at how fast things are orbiting. Why don't we notice? Why don't we see that motion? And it was there that Galileo used these wonderful examples. He says, well, if you're in a ship, in the hold of a ship, and there's no windows, and you have all these experiments you can do, anchor the ship and do the experiments, and then let the ship sail on an even sea and do the experiments, and they'll come out the same observably, right? The observable phenomena will be the same. I have the quotes in my book. You read out of it; it's beautiful. If there's water dripping down, if you release butterflies, when the ship is under sail, it's not like the butterflies will all crowd up at the aft, right? That was not Galileo arguing that there isn't a difference between a ship at rest and a ship moving. It was Galileo arguing there is a difference, but you can't directly see it. Don't expect it'll be obvious. And by analogy, we on Earth could all be moving together at a very high rate and not notice. Right? That was the point of Galileo. But then you say, all right, but now you're postulating this non-observable absolute motion. What good is that? What good could that be for physics if it can't observe it? Isn't that like postulating, fairies or ghosts or something you can't observe, right? How could that be part of science? And now we get Newton's answer. And again, he's very careful. This is very beautifully, systematically written. So if you look on page 2, third paragraph, having made all these distinctions, but we may distinguish rest and motion, absolute and relative, from one another, right? You can distinguish absolute motion from relative motion by their properties, causes, and effects. Properties, causes, and effects. 3 things. He then systematically goes through. It is a property of rest that bodies really at rest. Okay, so that's the absolute notion. Take 2 bodies that are at absolute rest. It is a property that bodies really at rest do rest with respect to one another. So they will also be at relative rest. If you're at absolute rest, if you have 2 bodies both at absolute rest, of necessity they will be at relative rest. And relative rest is observable. What does that mean? It means if I see 2 bodies in relative motion, I know they can't both be at absolute rest. I can get some information about absolute motion there. I couldn't tell which is absolutely moving and which isn't, or maybe they're both absolutely moving, but I know for sure they're not both absolutely at rest. Right? If they're in relative motion. Yeah.
I just did a quick check on the Scholium. Yes, indeed. There is the distinction, the definition of absolute time, the definition of absolute space. Then we go for absolute motion. Then we start talking about relative motion too. In between, it also defines space. But there, probably I just read too fast, but I'm not so sure if you can give the reason of why we cannot also have relative space. Because in the definition of absolute time, it's kind of implicit.
We do have relative space.
Okay.
He says, remember, I read this to you. He says, when he talks about space, he says that absolute space in its own nature, without relation to anything external, remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces, which our senses determine by its position to bodies. He's not denying there's such a thing. And that's what we use in everyday life. Right? We determine locations in everyday life as locations relative to certain objects treated as immovable. His point is they may not be immovable. Maybe they're moving.
Well,
yeah?
Yeah.
In the absolute sense. Okay, so we may distinguish rest and motion, absolute and relative, one from the other, by their properties, causes, and effects. And therefore, he says, if 2 bodies are at absolute rest, then they're certainly at relative rest. And therefore, as it is possible that in the remote regions of the fixed stars, or perhaps far beyond them, there may be some body absolutely at rest, but impossible to know from the positions of bodies to one another in our regions, whether any of these do keep the same position to that remote body, it follows that absolute rest cannot be determined from the position of bodies in our regions, right? We cannot look around us and observe anything that will inform us whether any body is at absolute rest. Okay? Now notice what he's saying. I'm postulating there is a state of absolute rest, and I'm telling you, you can't observe whether anything's at absolute rest. It is a property of motions that all parts which retain in their given positions to their wholes. So if I have a body and all of its parts are at relative rest, right? The parts of the body are not moving with respect to each other, do partake in the motion of those wholes. So even if I have a body and its parts are not moving with relative to each other, still the body as a whole and the parts can be moving. Right, let's just, again, he says we can distinguish them by their properties, causes, and effects. Now, what he says a bunch about the properties, let's leave that. Then he goes to the causes, down the next to last paragraph. The causes by which true and relative motions are distinguished one from another are the forces impressed upon the body moved. But relative motion may be generated or altered without any force impressed upon the body. Okay, so that's from the causes. Change in absolute motion requires a force. Change in relative motion does not. Right? What do I mean? All right, there we go. If I want to change whatever this thing has some absolute motion right now. We don't even know what it is. But if I want to change its absolute motion, okay, I've got to put a force on it. I've got to, that's change, whatever the absolute motion was, after I hit it, it was different. Right? I need a force to change a motion. That's Newton's fundamental principle. We didn't write it this way. We'll talk about this, but you've probably seen this guy, F equals ma. Okay, this this acceleration is a change in motion, in absolute motion. And in order for there to be a change in absolute motion, there has to be a force impressed on the body. But I can change its relative motion without impressing a force on it. Right? I mean, here's this body. Right now, it is in relative rest with respect to me. Its relative motion with respect to me is 0, right? I'm going to change it. Right? Now it's moving with respect to me. Right? It's now in relative motion with respect to me. I didn't put any force on it. I put a force on me. So you have to think about the causes and then and the effects, right? So he says true motion is neither generated nor altered, but by some force impressed upon the body moved. But relative motion may be generated or altered without any force impressed upon the body, for it is that relation may be changed in which the relative rest or motion of this body did consist. Sorry. It is sufficient only to impress some force on other bodies with which the former are compared. And by giving way, that relation may be changed in which the relative rest or motion of this other body did consist. That's what the relative rest and motion is. It's its relative rest or motion with respect to something else. If you put a force on the something else, you can change that without putting any force on the body. Right? So you can't change absolute motion without a force. You can change relative motion without a force on the body. Very important difference. For the same forces, if the same forces are likewise impressed on those other bodies with which the comparison be made, that the relative position may be preserved, then that condition will be preserved in which the relative motion consists. Therefore, any relative motion may be changed when the true motion remains unaltered, and the relative may be preserved when the true suffers some changes. Thus, true motion by no means consists in such relations. So that's from the causes. And now finally the big one, from the effects. The effects. I can distinguish absolute from merely relative motion by effects. The effects which distinguish absolute from relative motion are the forces of receding from the axis of circular motion. For there are no such forces in a circular motion purely relative, but in a true and absolute circular motion, they are greater or less according to the quantity of the motion. Now he proposes an experiment. Now, if I went back in New York, in my office, I have the experimental apparatus. Pretty simple. Tripod and a bucket. Okay, some water. I mean, Newton now brings into the middle of this discussion an actual experiment, and an easy one to do. It is not a thought experiment in the normal term of that. When people often say a thought experiment is often something which practically can't be done, right? No, it's an easy, I can do it, you know, I mean, you can do it, go home and do it. If you don't believe Newton, go check. This is a real experiment. Newton did it. Now, it's a kind of experiment you don't have to do because you know how it's going to come out before you do it, right? It's not like if I said, I don't know, take, you know, a tablespoon of cinnamon and then a half a tablespoon of baking soda and then some ground up aluminum and put them in a bowl and stick them in a microwave. Probably you don't know what's going to happen. I don't do that. I have not to. Right, so probably something nasty would happen. Blow up the microwave. Okay, that's an experiment where, you know, you'd have to now but you know enough, right? I just need to describe the experiment and you know how it would work out. This is also what Galileo did a lot. That Galileo would talk about experiments. Sometimes he actually did them, sometimes it's doubtful he actually did them. But whether he did them or not, our everyday experience of the world makes us already know how they'll come out. So this I've argued publicly, said publicly, and will defend, could arguably be said to be the most important experiment in the history of science. And you can do it at home. Why? Because it settles this dispute. Right? You might think, well, what kind of this is a fundamental dispute about the nature of space and time and motion. How can we settle it? And the answer is we can settle it by doing an experiment, and an easy one, and thinking. If a vessel, a bucket, right, hung by a long cord, is so often turned about that the cord is strongly twisted, then filled with water and held at rest together with the water. All right, so here's the experiment. Take a bucket, hang it from the ceiling or whatever. Hang it from the ceiling by a rope. Twist it, twist the rope very strongly. Here's the bucket. And in the bucket, put some water and hold the thing at rest for a while. Okay, step one. This is phase one of our experiment. Thereupon, by the sudden action of another force, it is whirled about in the contrary way. And while the cord is untwisting itself, the vessel continues for some time in this motion. The surface of the water will at first be plain, that is flat, as before the vessel began to move. Right? So in 2, we've twisted the bucket this way. We suddenly give a push to the bucket and it starts untwisting and falling down and spinning, right? And as it does immediately, what's now going to happen is the bucket is now spinning. It is certainly spinning relative to the water, right? So one way to think about this that's helpful to think about is imagine you do this experiment and you're an ant and you're floating on a little leaf, okay, in the water, inside. And in phase 2, notice in phase 1, there is no relative motion between the water and the bucket. Remember, according to Descartes, the motion of the water is just the relative motion of it with respect to its immediate surrounding or container, which is the bucket. So here, there is no relative motion of the water in the bucket. Here, there is. Right now, the bucket is spinning relative to the water, and reciprocally, the water is spinning relative to the bucket. And one way to think about that is if you're the ant, in phase 1, you can just look up, oh, there's the handle of the bucket. And in phase 2, you look up and you go, oh, look, the handle of the bucket. Right? You'd see that. because it's spinning relative to you and you're spinning relative to it. However, what Newton points out is that in phase two, the surface of the water is still flat. Let's go on. The surface of the water will at first be plain as before the vessel began to move. But after that, the vessel, by gradually communicating its motion to the water, will make it begin to sensibly revolve and recede by little and little from the middle, and the ascent to the sides of the vessel forming itself into a concave figure, as I have experienced. And the swifter the motion becomes, the higher will the water rise, until at last, performing its revolutions in the same times with the vessel, it becomes relatively at rest in it. So, phase three. Now, there is no, so here there is relative motion, right? In phase two. Here there's no relative motion. Here we're back to no relative motion. No relative motion. The bucket, now the water is concave. It does that. And you can see that. That is visible. Right? You can notice the water went from flat, gradually, as it were, seems to climb the side of the bucket. And eventually, when the water and the bucket are now at rest with respect to each other, so if you're the ant, now again you look up and you see the handle and the handle's just sitting there. Right? You are not in relative motion with respect to the bucket. Therefore, according to Descartes, you're not in motion. That's phase three. Then there's a phase four. This ascent of the water shows the endeavor to recede from the axis of its motion and the true and absolute circular motion of the water, which is here directly contrary to the relative. Right? There's absolute rotational motion and no relative motion, which is here directly contrary to the relative, becomes known and may be measured by this endeavor. At first, when the relative motion of the water in the vessel was greatest, it produced no endeavor to recede from the axis. That's right when you let go of it, there's a very rapid relative motion, but there's no tendency of the water to climb the sides. Right? It produced no endeavor to recede from the axis. The water showed no tendency to the circumference, nor any ascent toward the sides of the vessel, but remained on a plane surface. And therefore, its true circular motion had not yet begun. Its absolute circular motion had not yet begun. But afterwards, when the relative motion of the water has decreased, the ascent toward the sides of the vessel proved its endeavor to recede from the axis, and this endeavor showed the real, absolute circular motion of the water continually increasing until it had acquired its greatest quantity when the water rested relatively in the vessel. And therefore, this endeavor, the thing you can see, you notice sometimes the water's flat and sometimes it isn't flat, and you ask why. And your immediate answer is, oh, it does this when it's spinning, when the water is spinning. And now you say, spinning relative to what? Not spinning relative to the bucket. Because we have relative spinning here and no endeavor. And here we have no relative spinning, and here we have no relative. There's no correlation between the relative motion and the presence or absence of this endeavor to recede, or this climbing of the sides. And then there's a fourth point. After a while, what happens, and if you do this, this is true, eventually, as it were, the bucket, as we would say, comes to rest, but the water keeps spinning in it. So now we again have relative motion. And we have this shape. So here we have relative motion with this shape. Here we have relative motion where it's flat. Here we have relative rest with this shape. Here we have relative rest where it's flat. You cannot appeal to the relative motion to explain the phenomenon. And your thought is, oh, what explains it is it or is it not spinning? For Newton, that's fine. And he's going to say that's the absolute spinning. Is it absolutely spinning? But if you say, no, I mean, is it relatively spinning? Then the question is, relative to what? Not spinning relative to the bucket. Now, what relationists have tended to do in response to this is to say, okay, you're right, Newton. I mean, nobody disputes it. Newton's absolutely correct. This refutes Descartes. Right? Because Descartes can't explain this phenomenon. Now, relatives tend to not want to give up so easily. And as I said, there are all kinds of different versions of relationism or relativism you could try to come up with. Off the top of your head, you might say, well, it's not spinning, whether it's the water spinning relative to the bucket, maybe it's the water spinning relative to the room, right, to the walls of the room. And then you say, yeah, well, what do you think would happen if we sat the bucket here and put the room on a big turntable and spun the room around it? Would the water do this? And you already know it wouldn't. Or you go a little bigger. Maybe is it spinning relative to the Earth, the whole Earth? Well, if that were the relative motion, then there couldn't be any physical effects of the Earth itself spinning, because the Earth can't be spinning relative to itself. But there are effects of the Earth spinning. And you know there are, right? Whenever you see weather maps and you know cyclones go one direction in the northern hemisphere and the other direction in the southern hemisphere, why is that? It's because the Earth is rotating. Why is the Earth, why does it stick out a little in the middle? It's oblate, right? It's a little fatter in the middle and thinner this way. Why? Because it's spinning. That same bucket effect. If you've ever seen a Foucault pendulum, it's impressive, right? The pendulum is at rest with respect to the room, but as you watch it, what you say is, oh, the pendulum, its motion keeps changing, and you know, those little pins set up. I don't know if you've ever seen it. It's an impressive sight. You know, little pins set up on the ground, and if you wait a few minutes, you'll see that the path of the pendulum keeps turning with respect to knocking over pins. Right? You say, well, what's going on? Why is the pendulum spinning? The answer is it isn't spinning. The pendulum keeps going back and forth in the same plane. It's the Earth spinning under it. What you're seeing is the Earth spin under the pendulum. So it can't be that the relative motion, the relevant motion is the relative motion of the thing with respect to the Earth. Okay, then you can go even grander. Mach tried this, Ernst Mach, we're already in the early 20th century. I'll go all the way out to the fixed stars. The relevant motion is the motion of the body with respect to the fixed stars. Now that's already, okay, it's kind of a strange claim because, you know, the stars are pretty far away. You might wonder how that works. Mach never actually gave us a theory of how it worked. But he didn't like Newton's argument. He didn't like Newton's conclusion. Because he didn't like Newton's conclusion, he wanted to somehow find a way to deny it. And the best he could do is say, it must be the motion with respect to the fixed stars, without giving any theory of how that could possibly be the case. Little sidelight. Einstein, when he was young, was impressed by Mach. He liked Mach. He wanted a Machian theory, a relationist theory. And you might be excused for believing that the theory of relativity, because relative sounds kind of like relationist, is a fulfillment of Mach's ideas. It is. Theory of relativity is not a relationist. It's an absolutist theory. doesn't have Newtonian absolute space and time, but it's an absolutely zero. I mean, Einstein, the explanation of this experiment. What is the explanation of this experiment according to Newton? Briefly, the water does this instead of this when it's spinning. Spinning relative to what? Spinning relative to space and time themselves, if you will. The spinning is defined with respect to the very intrinsic structure of space and time, not with respect to any material bodies. That's the answer Newton gave. It's the answer special relativity gives. It's the answer that general relativity. It's the only answer we've ever had. So when I say this is the most important experiment, it's because the fundamental conclusion now, relativity is not Newton's theory. In relativity and special relativity, you change the account of space and time. In general relativity, you change it again. But through all those changes, it's still Newton's side that wins this debate. Now, Newton, when he gets to the end, so you have kind of two versions of this experiment that are discussed in the Scholium. And they're kind of the same point, but it's worthwhile thinking a little bit about it. To actually, I mean, this is a kind of complicated setup. It's not obvious, maybe, but this phenomenon of the water, and I hope everybody believes this is what the water will, if not, check. Okay, don't take my word for it. Get a bucket, check. Pro tip, get some food coloring. It's easier to see. Get some food coloring to put in the water and then sprinkle, some oregano or something that'll float. So it's easy to see what happens to the surface of the water. It does exactly this, right? As it spins, it slowly becomes concave. Why does it do that? Well, really, the reason it does that, the full explanation is a little bit complicated. It's important for this experiment that there be gravity. If you tried to do this in the space station, it wouldn't do this. It would actually, what would happen is once you got it spinning, instead of looking like that, it would look like this, that all the water would actually kind of form a cylinder on the outside, not this shape. So, gravity comes into this. It's a little bit, I mean, if you want to understand why it produces that shape, you kind of have to notice that it's sort of easy to see. Imagine I try to make this shape in a non-spinning bucket, right? I take a bucket of water and then I take a bowl and I stick the bowl down so that the shape of the water is now this shape. And I suddenly pull the bowl out. What'll happen? Well, the water will all rush, right? It'll all rush from the outside to the inside until it's all evened out. What does that mean? It means there are forces, when it's in this shape, there are forces that are pushing toward the center. And that's really because there's more pressure on this side than on this side. So there's forces toward the center, as we say, centripetal forces, center-seeking forces. And that's because of the gravity. If you take away the gravity, it wouldn't do that. So Newton at the end gives you another example of this when he says, look, this spinning, you can tell it's there. This absolute spinning, you can observe that the spinning is going on without there being any relative observable motion at all. So he says, last paragraph, it is indeed a matter of great difficulty to discover and effectually to distinguish the true motions of particular bodies from the apparent, because the parts of that immovable space in which those motions are performed do by no means come under the observation of our senses. So this is, again, apparent in apparent space and apparent time, that just means sensible. It means observable, right? Empirical. Absolute space does not come under the notice of our senses. Yet the thing is not altogether desperate, for we have some arguments to guide us, partly from the apparent motions, which are the differences of the true motions, partly from the forces, which are the causes and effects of the true motions. For instance, if two globes kept at a given distance from each one from the other by means of a cord that connects them, were revolved around the common center of gravity, we might, from the tension of the cord, discover the endeavor of the globes to recede from the axis of their motion. Right? So just stop. Suppose instead of a bucket and water, we have two globes, two spheres of metal, say, tied together by a cord. And you imagine this system is spinning around its center of mass. Then there'd be tension in the cord, right? If it weren't, there'd be no tension. They would just sit here and the cord would be slack. If you start to spin it, there'll be tension in the cord. And you can see and measure the tension. I mean, maybe you've got a spring or a device, a tension measuring device. The greater the tension, the faster it's spinning. So notice, without seeing the spinning, you know they're spinning. Why? Because you see the tension. You can compute the tension. If you know the mass of the bodies, you can compute then how fast it's spinning. So he says, and from thence we might compute the quantity of their circular motions. Right? We can figure out how fast it's spinning. And then, if any equal forces should be impressed at once on the alternate faces of the globes to augment or diminish their circular motions, from the increase or decrease of the tension of the cord, we might infer the increment or decrement of their motions, and thence would be found on what faces those forces ought to be impressed, that the motions of the globes might be most augmented. That is, we might discover the hindmost faces, or those in which the circular motions do follow. Now, if that went too fast, again, you're imagining you've got these two spheres, they're tied together by a cord, you have a measure of the tension. Now, you go in, there's no relative motion of anything, right? The two bodies are at relative rest. They're not getting further or closer together. Now you go in and you push, say this way, and watch the tension. If the tension goes down, then your pushing is slowing the rotation. And if the tension goes up, then your pushing is increasing the rotation. And you find, where do I push to maximally increase the tension? Those are the hindmost. Those are the following sides of the sphere. So now you know, oh, the spheres are not only spinning, not only do I know how fast they're spinning, but I know they're spinning this way, right? Here's the front, as it were, and the back. The spinning must be like this. All of that is experimentally determined, right? It is determined by observation, not observation of motion, observation of tension. How does the tension connect to the motion? That way. The faster it's spinning, the more they're accelerating. And the more they're accelerating, the more you need a force. That force is the tension. But the faces which follow being known, and consequently the opposite ones that precede, we should likewise know the determination of their motion. And thus, note this claim, and thus we might find both the quantity and the determination of this circular motion, even in an immense vacuum, where there was nothing external or sensible with which the globes could be compared. Right? Even in an immense vacuum, even if the only material objects that existed were these two globes and this cord between them, and they were at relative rest at all times, you could still tell that that whole system was spinning absolutely, how fast it was spinning, and in what sense it was spinning. by observations of the tension. But now, he says, and this is, he's doing this last little bit very quick, and it's a little subtle and it's a little dicey. Okay. But if we observe, but now, if in that space some remote bodies were placed that always kept a given position to one another, as the fixed stars do in our regions, we could not indeed determine from the relative translation of the globes among those bodies whether the motion did belong to the globes or to the bodies. Right? So imagine we add, we start with only the two spheres in the core. Now we add these fixed these stars that are at relative rest with respect to each other. Now we can see that the globes are spinning with respect to the stars, but equally the stars are spinning with respect to the globes, right? Again, relative motion is always symmetric. So is it really the globes that are spinning, or is the stars that are spinning, or is it both that are spinning, or what is it? He says, but if we observe the core and found that its tension was that very tension which the motion of the globes required, we might conclude the motion to be in the globes and the bodies to be at rest. And then lastly, from the translation of the globes among the bodies, we should find the determination of their motions. So that's kind of the suggestion. Notice the suggestion is, yeah, the fixed stars kind of come into this, but not because it's motion with respect to the fixed stars. That is motion. The motion is absolute motion. It's there no matter whether the stars are there or not. But it's kind of a suggestion that you might have reason to believe these fixed bodies are at absolute rest. And if they are, then their relative motion is their absolute, right? Relative motion with respect to bodies at absolute rest is absolute motion. But last sentence, but how we are to obtain the true motions from their causes, effects, and apparent differences, and the converse shall be explained more at large in the following treatise, for it is to this end that I composed it. So he's perfectly aware that what he can directly observe are, first of all, relative motions. He can observe those, but he can observe more than that. He can observe forces. He can observe changes like this, right? He can observe causes and effects of things. And he thinks that from all of what he can observe, he can make an argument, a plausible argument, about what the absolute motions are. But it's not a proof. He knows it's not a proof. I mean, Newton literally proves, once he lays down his laws of motion, he proves as a lemma that no observation can determine with certainty the absolute motion of any object. Or he essentially proves what Galileo already had suggested. Do any experiment you want in a laboratory at absolute rest, and then repeat that same experiment in a laboratory moving uniformly, in uniform motion. The outcomes will be observably the same. So there's no way you can do an experiment that will tell you which of those two situations were. That's actually a theorem under certain conditions of his own physics. So, the relationship between the absolute and the relative motions is subtle, and it's not one where even if you observe all the relative motions that you could infer with certainty the absolute. But he still thinks there are pretty reasonable arguments that can be made. And at the end of the day, for his purposes, he actually doesn't have to get to the absolute motion. Because he's going to be able to explain what he wants to explain without determining them precisely. Like what? The orbits of the planets, things like that, right? The apple fall. Okay? So Newton's whole scientific account of these phenomena that you get out of the Principia are based on the postulation of absolute space, absolute time, and therefore absolute motion. And that these exist independently of matter. And Descartes and Leibniz absolutely did not like that. I mean, Leibniz, in the Leibniz-Descartes correspondence, he's going on and on about how terrible absolute space and time are. These fantasies of Newton's, right? Now, when I say, if you want to go read it, I mean, there's the number of passages about space and time. It's not the whole thing. There's a bunch of other things that come in. When you read it, as I say, it's a little bit frustrating because as soon as Leibniz attacks Newtonian absolute space and time, what Newton would have responded with was with the bucket. And for some weird reason, Clarke doesn't get to the bucket until letter 4. You know, he talks about after definition 8, the Scholium to definition 8 or something. And I, you know, there's reason to believe that Newton was like tearing his hair out, saying, "What are you doing?" Here's the argument. Why aren't you giving the argument? And after all of this, it's just painful to watch Leibniz. Leibniz, for this entire thing, has been saying all motion is relative motion, all relative motion is relative motion, all motion is relative motion. And then Clarke finally brings up this argument, and Leibniz says, well, of course there's a difference between real motion and merely relative motion. And you're going, well, you know, you've been, your entire argument has been that there is no, you know, that there is no absolute motion, and then Leibniz said, well, of course there's, you know, a difference between, and that has to do with cause. And so you're going like, anyway. You can't approach the question, even today, of the nature of space and time without having this phenomenon in mind, right? Whatever story you come up with at the end, it better be able to explain this experiment. And if for some reason or other you're inclined to want to be a relationist, not believe in absolute space and time, you have an immediate task, because you see, I mean, what we will see is how Newton, and then in a different way, how Einstein appeal to absolute spatiotemporal structures to account for this. And if you want to deny that those structures exist, then you've got the job of giving me an alternative explanation. Okay. Now, all of this, of course, doesn't prove that Newton was right. And if you go to relativity, you're going to say Newton wasn't right in all details. But in his argument against relationism, that, you know, Einstein is that theory is on the same page, and in general relativity, that theory is on the same. Okay. Now we have officially 15 minutes left. I could say a word about what was going on with Leibniz, although it's not exactly completely relevant to this, but it might be later. Or are there any questions or any things that I've talked about that people want to go into more detail yet?
Maybe I'm misunderstanding what's going on here, but it seems to me that his notion, Newton's notion of space is one that even goes beyond like physics, right? In the sense that in day-to-day physics, one doesn't try to even approximate anything like absolute space or something, right? Like it's just it seems interesting to me that it seems that maybe Newton here is going even beyond what is like useful. He sees science more as something that goes beyond what is sort of practically useful.
So let me try and respond to that. I mean, the full nature of this response will not be clear for another few days, but let me at least say something that would suggest that what Newton's doing here is not so distant. It's not beyond physics or whatever. So even today, suppose a physicist says, look, I'm going to specify a certain experiment, to do a certain experiment. They tell you, get this apparatus, that apparatus, set this up this way, blah, blah, blah. Okay. Either directly or implicitly, they will, unless they're doing something strange, they'll say that they will either say directly or implicitly expect you to do this in what we would call an inertially, a lab that's in an inertial system or an inertial mode. As opposed to what? As opposed to a lab that's spinning. Right? I mean, a spinning room, you can make, I mean, I take it every, maybe, you know, you could go to amusement parks where they have these big cylinders, right? And you pay money and you get into this big cylinder and it starts spinning and it spins faster and faster. And then you feel, as we say, you feel a centrifugal force pushing you back against the wall, right? And you feel pinned to the wall. And then they drop the floor and there you are, you know, you're pinned to the wall and you see your friend over there, they're pinned to the wall and everybody's, you know, if you turn your head, you, okay. Don't do an experiment in that particular cylinder unless you're explicitly told to, won't come out right. Okay. That effect of spinning is the very effect that Newton's pointing to. Anytime, even in present day physics, when you either explicitly or implicitly demand that you do an experiment and it not be in a spinning environment, you're appealing to the very distinction that Newton is making. And when you say don't do it in a spinning lab, you don't mean don't do it in a lab that's spinning with respect to this or spinning with respect to that. Just don't do it in one that's spinning, period, full stop, spinning. That's an absolute distinction. Spinning and non-spinning is an absolute distinction. It's an absolute distinction for Newton. It's an absolute distinction for Einstein, right? Difference between spinning and non-spinning. So that part of, and that's, you know, that's the heart of this bucket argument. So he's not going beyond physics there. Now, I'll say another couple of words because this can get very confusing. And you immediately see how confusing it is. Because in everyday life, in like, you say, oh, when you're in a spinning room, there's a centrifugal force, centrifugal force, center fleeing force, right? Fugo. A force pushing away from the center. But how could there be a force pushing away from the center? Where's it coming from? I mean, you're in this thing, there's at the center, there's nothing there. It's just empty. It's empty. Not being pushed back. There's no centrifugal force. You're being pushed forward. What you feel is the force of the wall on your back pushing you toward the center. It is a centripetal force, a center-seeking force. The same force that these two rotating globes is produced by the cord between them, an inward force. That's what's really going on. And if you learn your physics carefully, you'll be told centrifugal forces are fictitious forces, which means they don't exist. Right? That's what fictitious means. So it's a kind of complicated situation because people aren't very careful in describing what's really going on. But that distinction between inertial and non-inertial, or spinning and not spinning, that's not going beyond physics. We need that today. right?
I don't know how would it be possible to ask this question. Maybe it's a nonsensical thing, but just imagine that there is another world exactly and ultimately identical with the world that we are now living. Now we could ask this question, about the motion in these two worlds. I think that the relations would say, no, there is no motion because these two worlds are completely identical, and every change, every motion in these two are identical. So I cannot imagine any kind of relation between these two that finally lead us to have a sense of emotion because they are completely identical. On the other hand, if you ask the same question from a person who believed in Newtonian conception of motion, based on whatever we said, he might say that everything is moving in these two.
Yes.
In these two worlds.
I mean, let me rephrase what you're saying.
Okay.
I think this is what you have in mind. According to Newton, I mean, take the entire world as it is, full of matter, doing everything it's doing, right? Imagine an alternative world, not the actual world, but an alternative physically possible world, according to Newton, where, as it were, it looks just like ours, only all of that stuff is moving again, with uniform straight line motion. It's like in Galileo's ship, right? Everything is in absolute motion. In the first world, let's say, mostly the stars and everything are at absolute rest. But in this world, the stars themselves are moving, but moving at the same rate, right? So there's no relative motion, but the whole thing is moving. Yeah, Newton would say that second one is a way the world could be that is physically different from ours. Why? Because in ours, the things are at absolute rest, and in that one, they're not. But there would be no experimental or observational signature, right? From the inside, the world would look in all respects the same. That was Galileo's point about the ship, right? That the ship's sailing at a constant rate over calm seas. If you're in the ship, everything's going to look the same. Now notice, by the way, Galileo specifies that the ship has to be on calm seas and moving uniformly. You can't be turning the ship. The ship can't be, in a rough sea doing this. Then you'd notice, right? The ship can't be spinning, right? Then you'd notice. But if the ship is sailing smoothly, that will have no observable effect. So yeah, the relationist wants to say the reason there's no observable difference there is that there's no difference. If all motion is just relative motion and all the relative motions are the same, then it's the same situation. They're not two different situations. And Newton is forced to say, no, these are two different situations. And you couldn't tell the difference by any experiment. Now, you have a question, which is how upset are you by that? And there are two answers here. One answer is, I'm really upset. And the other answer is, that's life. Okay? There can be facts that we can't determine what they are, right? There can be unobservable facts. Which road you go at that fork will determine a tremendous amount about you as a philosopher. Okay? One road leads you to a kind of empiricism, radical empiricism. To be a difference, something must be observable in order to be a difference at all. The idea of an unobservable difference is somehow incoherent. You could kind of find reasons for that in Hume and some of the empiricists. The other direction is like, that's life. We shouldn't be so surprised that there are some things we can't determine by observation. What we should actually be surprised about is that we can determine anything by observation. What makes you think you're going to be so lucky that every question you'd like to have answered, you can go do an experiment and figure out the answer, right? That, you know, who set up the world for your convenience? And you kind of have in your own mind to make a decision which side of that you're on. Now, I'll just be straightforward. I'm obviously on the second side. I think the universe has no obligation to make itself transparent to us, even on issues that we're mightily interested in. Okay, tough luck for us. I mean, okay, suck it up. That's life. You know, if you haven't been disappointed by life yet, you're lucky. You're going to be disappointed in lots of ways, and this is one of the ways you could be disappointed. You know, there's some philosophers who just have this other view. I mean, it's like the people who are freaked out by Gödel's theorem. How, you mean there are mathematical facts we couldn't know? Okay, yeah, why not? Lots of mathematical facts out there. Most of them are kind of trivial. What makes you think every mathematical fact we could prove or disprove? I mean, to me, that's just weird. It's like, why think that? Our access to the world is limited in many different ways. But yeah, your example is exactly the example that Leibniz used. Leibniz says, yeah, I have 3 minutes, so I can bring this in. Leibniz, and it's a weird thing because these examples are actually introduced originally by Clarke to defend Newton, and then Leibniz picks them up and kind of modus ponens and then and tries to use them against Newton. But take an example. Take the entire universe as it is, with all the matter and all the planets and everything, blah, blah, blah. Now, imagine a different world, not that's in motion now, but just much simpler. Everything was moved over in absolute space. You're Newton. Take everything and move it three feet over in absolute space. That'll be a possibility too, right? The world could be like that. No experiment will tell you, right, will distinguish those two. That's just, or to use the example that Clarke uses, he says, take the universe and just twist it 180 degrees, right? Twist east for west, twist everything around. He says, look, it's a different world. Because look, I twisted it. It's different. It looks the same. All the relations are the same. So according to you, Leibniz, it's either the same world, but they're not the same world. Because look, I twisted it around. And Leibniz just says, no, you don't see any difference. And therefore, there can't be a difference. This is the so-called identity of indiscernibles thesis. If they're not discernible, then they're not different. You, Newton, are committed to indiscernible differences, but I don't allow them. And the Newtonian response is, of course I am. And then there's a back and forth with these examples. And then Leibniz brings in the principle of sufficient reason. I mean, I've got half a minute to do the principle of sufficient reason. Leibniz says, look, Newton, you have this problem. We both agree, we're good Christians, right? Well, he doesn't think Newton's a good Christian. But anyway, we both agree, we believe in the Bible. So there was a moment when God created the material universe, right? Now, according to Newton, before God created any matter, there was still space and time. Absolute space and time was there, ticking along actually for an infinite period of time. And then one fine morning, God decides, today I shall create matter. Let there be light, whatever, right? And that's what Newton thinks. And Leibniz says that violates the principle of sufficient reason. Because God could have no reason to do that act on that at that particular moment of absolute time, as opposed to any other before that, because it was just an empty universe, nothing going on. So that would require God to violate the principle of sufficient reason, and even God cannot violate the principle of sufficient reason, says Leibniz. That is the fundamental principle of metaphysics. And he's serious. I mean, Leibniz literally says, and you can do some interesting theology and theodicy with this. If God had before him in his mind 2 different possible worlds to create, and he could not find a reason why one was better than the other, which if you imagine, I'm either going to put the universe here or put it there. Okay, they're equally morally good, right? It's not like there's a good neighborhood and a bad neighborhood in absolute space. He says if there's not a moral reason why one is better than the other, then God will create neither. Because to create one, he would have to violate the principle of sufficient reason. Now, this is a weird situation. It's like he said, God wants to create a universe. He really wants to, but he can't. He's stymied. I can't create this one because that one would be equally good. And I have no reason to choose this one rather than that one. That actually starts Clarke as being itself blasphemous. He says, no, God can just decide. God can just, by an act of will, create one. You're putting yourself and your principles over God, right? So now you get a whole theological debate. Anyway, there's a lot in that that isn't really relevant for understanding relativity. So we're not. Okay? So I hope the force of Newton's argument has gotten across to you, even if you don't like it. It's something you have to contend with. All right? How do I explain that bucket? And so we'll pick up that next time.